Now, let's start discussing another important application in data transformation, encoding categorical variables. This technique is widely used in practice because many real-world datasets use text instead of numbers. For example, a dataset might use red to represent a color instead of using a numerical code like 0. Since machine learning algorithms don't naturally understand text, we need to convert these categorical values into numerical ones so they can be processed. That's the essence of encoding categorical variables into numerical variables. First, let's look at the first solution, label encoding. Simply put, with label encoding we directly assign a unique integer value to each category. In effect, we're defining what each integer means in physical terms. All we need to do is keep track of the mapping, so that when we decode later, we can translate each integer back to its corresponding categorical value. Specifically, label encoding is more suited for ordinal data rather than nominal data. Ordinal data means there's a natural order or ranking between the different categorical variables. For example, low, medium, and high are common examples of ordinal data. To better understand why label encoding is more suitable for ordinal data rather than nominal data, let's use nominal data as an example. Clearly, there isn't any inherent order or ranking among red, green, and blue, which makes them a common example of nominal data. If we simply use 0, 1, and 2 for red, green, and blue, respectively, we might run into some problems. For instance, assigning these numbers suggests that there's an inherent order or distance between the colors. The model might mistakenly assume that the difference between red 0 and green 1 is meaningful, or that green is somehow closer to red than blue 2 is. But colors like red, green, and blue don't have a natural order, so this could lead to misleading results during training. The problem is that for nominal data, label encoding can unintentionally create an order where none exists. Since the model works with numbers, it might try to find meaning in the order of 0, 1, and 2, learning patterns based on those values even though the colors should be treated equally. This can lead to misleading results during training. Therefore, if we're dealing with nominal categorical data, we should avoid using label encoding because it can introduce extra interference that negatively affects our machine learning task. However, if the data consists of ordinal categories like low, medium, and high, it's natural to use unique integers and their inherent order to represent these values. So, label encoding is more suitable for ordinal data. Now, let's look at an encoding scheme that works well for nominal data, one-hot encoding. With one-hot encoding, we create a binary column for each category. For example, if we have 3 colors, we create a vector with 3 elements. Each element corresponds to one color. Say, the first element indicates whether the color is red, the second indicates whether it's green, and the third indicates whether it's blue. In a one-hot encoded vector, the different elements aren't ranked by their positions, so we avoid the pitfalls of label encoding where certain colors might get unintentionally prioritized over others. What are your thoughts on the disadvantages of one-hot encoding? I believe this drawback is pretty obvious. If you don't have any intuition yet, take a moment to carefully analyze the encoding result and think about what might be wrong with it. To ensure every color is treated equally, we need to create a vector with as many elements as there are colors. If we have 100 different colors, our one-hot encoding will generate a 100-element vector, which significantly increases the complexity of the dataset. In practice, because datasets often have many data points, applying one-hot encoding can lead to a dimensionality explosion. This not only raises the cost of the machine learning task but also slows down the training process, potentially creating a workload that can't be completed in a reasonable amount of time. Next, let's look at another encoding scheme that helps avoid the problem of dimensionality explosion. We call it frequency encoding. When you have a large number of data points, you can calculate the frequency of each color and use that frequency to represent each color. It's a very straightforward solution. However, this method still brings some issues. For instance, it can be very sensitive to the data distribution. If the dataset contains a large number of instances for one particular color, that color's frequency will be very high, causing the model to potentially overlook other colors. Similarly, even though frequency values are decimal numbers between 0 and 1, they still imply an ordinal relationship. So when using frequency encoding, you need to pay special attention to the dataset's distribution. Frequency encoding works best when you have a large dataset with a fairly even distribution. Finally, let's look at an encoding scheme that can incorporate ordinal relationships, target encoding. In target encoding, we replace each category with a numerical value that is derived from the target variable. For example, if our target is to predict house prices, we can take a categorical feature like neighborhood and replace each category with a numerical value derived from the target, say, the average house price for that neighborhood. We calculate the average house price for each city, then use that average to replace the categorical variable representing the city. The most common metric here is the average value. Sometimes, we might also consider using the mode, which is the value that appears most frequently in the data. This method makes it easier for the model to capture the information we need, and the ordinal relationships among the numerical values are exactly what we're looking for. Based on our discussion of the advantages of target encoding, do you have any intuition about its potential disadvantages? The biggest issue with target encoding is that it can lead to target leakage. When the dataset has plenty of data points, computing the average for each category might reflect a strong ordinal relationship. If we then directly provide this ordinal information to the model, it's almost like we're helping the model cheat. We're essentially telling it what the pattern is supposed to be. This results in the model performing exceptionally well on the training set but poorly on new, unseen data, since that cheating information won't be available. This problem, known as target leakage, is something we must be very careful to control and avoid in machine learning tasks, because our goal is to deploy a model that makes accurate predictions on new data, not just on the training data. Finally, let's briefly discuss why encoding categorical variables is both necessary and important. This is an open-ended question, so when someone asks you about it in the future, you just need to provide a rational explanation. Essentially, encoding helps solve the fundamental problem of converting non-numerical data into numerical data without introducing unnecessary noise.